Hi, welcome back. In this lecture, we're going to talk about actually calculating the components of the traditional demand analysis. One of the papers you have for this week is actually by Lawrence Brown, Brooke Lerner, Baxter Larman, Todd Legaskets, and Mike Tagman. And they actually took a look at utilization of this historical way of doing demand pattern analysis and looked at the accuracy of it. One of the things they found is that the predictions were accurate between 10 and 19% of the time, which is a very low rate. However, from the financial standpoint, it can be a concern that the system would have been overstaffed between 75 and 86% of the time. That's also a concern. So we'll look at some other methodologies that can potentially be a little more accurate in terms of staffing. But we want to start this week by looking at these specific components. So I'm going to start out, and I'm just going to show you how they would be calculated if we were doing it simply from a paper perspective. If we're looking at the average, we simply take the average. So I would take each of these component times, the 6 minutes on March the 15th, 2006 through July the 26th, 2006 at 7 minutes. Each of those values, would add all of those values and then simply divide by the total number of values. Now, and that would give me an average of 4.95. So that's the average number of calls we experienced over that period of time. Now, another thing I can do is actually look at the standard deviation. So in other words, not only what was the average, but how much was were the number of calls likely to deviate in a given day. And the interesting thing about standard deviation is you may have seen this rule before, but a rough rule is if you have a normal distribution. With a normal distribution, 99.7% of the data is expected to fall within 3 standard deviations of the mean. So if we went out, we calculated the standard deviation and went out 3 standard deviations in each direction, well, that would give us a really wide range. Unfortunately, that may help us in terms of planning to make sure we have enough resources to always cover any capacity that may arise, but it would be a very poor model for predicting because we would be staffing at a much larger level than we need to, a large percentage of the time. Another problem is that the normal distribution is usually created by continuous data. And we're not talking necessarily about continuous data. We're talking about count data. And count data actually follows a very different distribution, something known as the Poisson distribution, which we'll come back and discuss next week because that will play a component or be an important piece, a component of the queuing theory model that I'll introduce you to next week. So standard deviation isn't a great measure, doesn't do a whole lot for you. Quite often, as you saw in a previous lecture, people will calculate it and actually place it at the bottom of their demand analysis, but it doesn't play a real important role. The next number is the maximum, and it's simply to look at the maximum. And if we look at the maximum here, I see it didn't show up on the slide, but I see 8 as being the largest number on 5/17/2006. That looks like the largest number that we had. 8 is the largest number, so 8 would be the maximum in this scenario. If we look at the high average as calculated by Stout, again, to simplify the computations, he took and he divided the total set of data into 4 different groups. He took the largest number from each of the groups. He took and added those 4 numbers and divided by 4. And as you see here, the high average is 7.5, but we would actually round that up to 8 because we can't really have half of our request. The average peak is very similar. We would take and only divide it into 2 groups. We would take those 2 groups of, in this situation I have 8 that would fit on the slide. So if if you did 20 weeks, you would have 10. You would take those and average the averages of those two groups. You see each group has an average of 8. We add those two averages together, divide by 2, and you see we get an 8. So there you see our primary calculations: the average, the high average, and the average peak. So then you can look at those and you compare them to the values that exist. You can see definitely if you based your deployment model and schedule and number of resources simply on the average, then quite often you're going to be understaffed. Where on the other hand, if you use the maximum of 8, then quite often you're going to be overstaffed. So here are the specific formulas, and I put these in so you could see them in the slides, in the handouts this week. But we have to manipulate these just a bit from the way they show up in the article to actually work with Microsoft Excel. So I wanted to run through that quickly as we wrap up this week so that you can see exactly how this is done. In kind of the newer version of System Status Management, they've dropped back to using basically 3 measures, maybe 4. These include the average peak demand that you see outlined here, and these are the ones that are actually covered in the academic article that you'll have. But you see the average peak demand, the smooth average peak demand, and the 90th percentile rank. With the average, of course, is simply the average. In Excel, to do that, you start out with the inputting equals, and then type in average. And when you type in average, it should come up with an initial parenthesis. Within the parentheses, then you would highlight the cell range. And you see here cell 5 through cell 24 is the range that's going to be actually added. And it will provide you the arithmetic average for that range. With the average peak, what we're doing is we're taking again and dividing that number of weeks into 2 sections, and then each of those 2 sections will then be divided by 2. So we take the maximum of C4 through C14, and we also take the maximum of C15 through C24. We add those 2 numbers together and we divide by 2. So you see, to do that in Excel, we do equals, parentheses, max, and then you see you'll have a parentheses automatically pop up when you type that max in. You input that cell range, you put the closed parentheses, plus max again, parentheses will pop up again, and now you add the second cell range from C15 to C24. Then you add the correct number of closing parentheses, which would be 2 there, and then divide by 2. Now with the smooth range, it's a bit different than the initial measures that Stout utilized. With this smooth peak, what is done is to actually look at each of the hours on either side of the hour in question and include them almost from a weighted average perspective as part of the calculation. So as you see here with the smooth peak, we're taking 20% of the 11 o'clock hour, and then we're taking 60% of the midnight hour, and then we're taking the last 20% to average out to, or to add up to 100, taking the last 20% of the 1 o'clock hour, and adding those 3 components together. So you see the average peak would have to be calculated for each of those before. So I made an assumption that the average peak at 11 was 6, at it was 7 at 11 o'clock. We had calculated it already for the midnight hour at 8, and for the 1 o'clock hour, we'll make the assumption that it's 6. So you see 20%, that's equals, and then parenthesis 0.2 for 20% times A26, which is the 7, then parentheses plus parentheses 0.6 times C26, which is the average peak we had calculated for the midnight hour, close parentheses, plus open parentheses, 0.2 times D26, which is 6 for the average peak at 1 a.m., and then close parentheses, and that should give us the smooth peak. And you see the smooth peak was actually 7.4. Now the 90th percentile, a little easier to do because it's actually a built-in function. So here you can see we simply type in percentile.exe. When you do that, it'll come up and you'll see as in the bottom example there, it'll say array, comma, K. K being the percentile that we want to look at, what percentage we want to look at. If you wanted the average again, you could put 50 there and it would return the average number again. But we want to look at the 90th percentile. So we put in the range of C4 to C24. The comma's already there. And then we add 0.9 for 90% within that last closed parenthesis and hit enter. And when we do that, it'll give us the final number for the 90th percentile. Here's an example of what that may look like again for each of the 24 hours in a given day. And again, you would have 7 of these, one for each day of the week. Again, remember these assumptions, or remember that a big assumption that's included with these calculations is that each call takes exactly 1 hour. So think about how that would influence the availability of your ambulances if these calls last more than an hour. Well, definitely, if they're lasting more than an hour, we're definitely going to need more resources than what we calculate. On the other hand, if they only last 20 minutes, then we would only need a third of the resources. Well, next week we'll look at something called queuing theory that actually takes that into consideration. Here you see all of these times represented for that 24 hours, and this is an example of a Wednesday, and you can see where the average falls and where that falls in comparison to the other measures, such as the smoothed average peak. So you'll be able to see that a little closer in the handouts. Here's another example. Some people like to actually utilize bars for part of the analysis and then put max average and standard deviation above that. A lot of different display methodologies that you'll see. Well, I'm going to stop there. This week I want you to actually spend some time, do these calculations, make sure that you're very clear on how they're done, and next week we'll pick up and we'll take the next step in actually designing your deployment model. In the meantime, if you have any questions, feel free to post them on the Facebook group or give me a call. Thanks.